systems, filtration systems, rainfall, and sustainable urban drainage systems. The method or combination of methods used to recharge an aquifer depends on the local conditions. Aquifer recharge methods are well spread and developed. In Europe, these methods play an important role in the drinking water supply, mainly because of their potential to treat water and attenuate undesired substances. In Australia and the United States, aquifer recharge methods are used to create a buffer of water for further usage during dry seasons, for non-potable and indirect potable reuse. In arid and semi-arid regions, due to high evaporation rates, subsurface storage of water becomes a major alternative over surface storage. The storage provided in the upper meters of soil and in shallow aquifers is an important water buffer and may be feasible for the implementation of low-cost technologies, such as sand dams, key lines, contour bunds or ridges, check dams, and terraces. The application of these techniques creates
A few other vulnerable areas are highly vulnerable aquifers and significant groundwater recharge areas. There are no policies in the local source protection plan to regulate threats in these areas, as our plan only deals with significant drinking water threats based on provincial guidelines. Threats in these two areas can only be low or moderate. There are 22 prescribed drinking water threats under the Clean Water Act, which are addressed through the Drinking Water Source Protection Program. 20 of those deal with impacts on water quality, and 2 deal with water quantity. The threats span multiple sectors, such as municipal, industrial, residential, and agricultural, so nobody is really exempt.
This is Matt and his dog Buddy. Hey Matt, deep water is safe and reliable. Still, it's just as important to keep the sources of our water abundant and as free from pollutants as possible. Did you know that Ontario has a drinking water source protection program to help protect your health and mine? Areas close to municipal wells and areas
1/3 of the U.S. freshwater usage. The area under the ground where groundwater is stored is called an aquifer. Some areas of the world have aquifers that are large and filled with lots of water, and others have no aquifers. What are the ingredients for a good aquifer? Rocks with high porosity and permeability in an area with a lot of rain. Under Earth's surface, there are rocks. Atop those rocks are soils. Some of those rocks and soils are made of gravels and sand grains with empty spaces called pore spaces between the grains. Some rocks are made of intergrown crystals with no pore spaces. These rocks may have open cracks or dissolved channels within them. Whether pore spaces or cracks and channels, the amount of open space in rocks that is available for air or water to fill is called its porosity. The more porous a rock, the more water it can contain. However, just having space doesn't mean groundwater can get into that space or out of it. These spaces have to be connected in a way that allows water to flow between them. Nearby rivers, and the water can move down into porous, permeable rock and collect there. We have a good aquifer. We can drill or dig wells into the aquifer and pull or pump out the water to use it for drinking or agriculture or whatever our need. However, we have to be sure that as we remove water from the aquifer, it's filling up at an equal rate. What happens if it doesn't? The aquifer dries up, and the pressure of the overlying land can squash the rock and soil, closing up cracks and pores and reducing its porosity and usefulness as an aquifer in the future. We call the saturated portion of the rock in an aquifer, the part that's filled with water, the saturated zone. The portion of the aquifer that sits above this zone might be a little bit wet, but does not have its pore spaces filled with water. Most likely, they're filled with air. We call that region the unsaturated zone. The boundary between these two zones is known as the water table. As you can see in this figure, the water table is not at the same level throughout the aquifer. It will be higher where the land above it is at a higher elevation, and lower where the land above it is at a lower elevation. And just like rivers on the surface, groundwater will flow downhill in the aquifer due to gravity, albeit more slowly than a river as it has to migrate through small cracks and pore spaces. Rivers move at speeds of about a foot per second, while the fastest groundwater moves at a rate of a foot per day, and the slowest groundwater is moving at a foot per year or decade. The other factor that influences groundwater flow is differences in pressure or the overlying weight of the rock. Groundwater will flow away from the area with the greatest pressure above it, the greatest weight of overlying rock, and toward the area with the least pressure, the lowest weight of overlying rock. When the water table is higher than a river, groundwater will flow into the river. We call that a gaining stream. When the water table is lower than the top of the river, then water from the river will soak into the ground and move into the aquifer. We call that a losing stream. As streams and rivers wind through various land regions on their way to the oceans, they may change from losing streams to gaining streams and back again depending on the water table of the land through which they travel. What happens when we remove water from the aquifer? How does that impact the flow of groundwater and anything that the groundwater carries? Notice the water table drops around the well itself. We call that a cone of depression. This cone of depression forms because we've pulled water out of the aquifer at a greater rate than the groundwater can recharge in this zone. Remember, groundwater moves only as fast as a foot per year depending on the permeability of the aquifer. So to recharge this region of the aquifer, we would need to be sure not to pump faster than the recharge rate. If we do pump faster, the water table drops down around the well as you see here. Let's look at an example of a very similar hillside and river system to our last image. Notice that as the well removes water, the water table drops around the well itself. In this case, it dropped down below the level of the nearby stream. So the groundwater on both sides of the well will move towards the well, as that's downhill for the groundwater. Notice that the stream itself is still receiving groundwater from the land on its right, but it's losing it to the land on its left. We would therefore expect the stream level to drop. The region to the left of the well would normally be moving down towards the stream, and it's still moving in that direction, but now with a steeper gradient and ending at the well. Finally, notice that the contamination dumped in the soils up the hillside is being pulled along with the groundwater towards the well. The downhill flow of water, whether in a lake or two aquifers, we call the top one in this image an unconfined aquifer because there's no barrier at its top that prevents water from moving up or down. So far, we have looked only at unconfined aquifers. But under the top aquifer in this image, there is a layer of impermeable rock that creates a boundary. None of the top aquifer water can move down across that boundary, and none of the water below can move up. We call that boundary a confining layer, or an aquitard. Because the rock layers in this area are folding or bending upwards to the left, any water that soaks into the ground up here, to the left of this rock layer, will make its way into the ground and collect in an aquifer under the confining layer. We call that a confined aquifer, and it has its own water table separate from the unconfined aquifer atop it. The water table of a confined aquifer is also known as a piezometric or potentiometric surface when it's extended over land that sits above the confining layer. We can think of this surface as an imaginary level to which water in the confined aquifer would rise were it tapped by a well. We can also refer to the confined aquifer here as an artesian aquifer because the water level is higher than the aquifer in this location. Notice what happens when we drill wells into different parts of this system. This well on the far right was drilled into the unconfined aquifer downhill of the stream. It pulls only water from the top aquifer and will draw that water and anything in that water from up the hill. This well was drilled up the hill from the first one, and it was drilled through the unconfined aquifer and into the confined aquifer below. It was drilled at an elevation that exactly matches the water table level of the confined aquifer. Once this well is drilled, therefore, water from the confined aquifer will rise up to the surface and sit there in the well structure at the water table level. We call that well an artesian well because it is produced from an artesian aquifer which was under pressure. This third well was drilled in between the first two wells and also down through the unconfined aquifer and into the confined one. Its surface sits below the water table of the confined aquifer. So as soon as this well is drilled, water will automatically start pouring out of the ground under high pressure and will continue to do so until the water table of the confined aquifer drops below this level. What's making the water flow? The hydraulic head. The pressure over here on the left at the water table is higher than the pressure over here at the surface. That higher pressure pushes the water up the well and out onto the surface. If no wells were drilled here, but there was a natural crack in the rock above the confined aquifer, that crack would become a natural exit with flowing water, and we'd call it an artesian spring. Note, a normal spring exists when we have a perched water table, or a perched aquifer, which occurs when an aquitard exists under an aquifer and is perched up a hill. The place where the aquitard intersects the hillside will be a place that water naturally seeps out of that hillside from the aquifer atop it and moves down the hills. This image from the Sierra Nevada mountains in California shows a spring coming out of the hillside. The water in that spring is coming from a perched water table. Some aquifers exist in ground very close to the ocean. In such cases, the aquifers might very well have salt water at depth and fresh water sitting atop. The more fresh water that exists in these aquifers, the more pressure on the underlying salt water, which keeps it from intruding too much and mixing with the fresh water, ruining the fresh water supply. What happens if the fresh water in this aquifer is overpumped? The pressure on the saltwater portion will be reduced, and that can cause the saltwater to intrude further into the aquifer. Understanding the geology below the surface is necessary for understanding the type of aquifers you have, the direction water will flow, and the potential purity of that water. Aquifers made of very small grains of sand have very slow water flow, but do have the added benefit of trapping contaminants and cleaning the water as it moves through the ground. Water that sits in giant caverns in underground limestone caves will move much faster, but anything added to that water as it moves through the system will collect. That includes oil, gas, and trash. Much of what we just described about groundwater also applies to the movement of oil and gas underground, except in the case of oil and gas, the fluids migrate upwards, not downwards. Oil and gas are fluids that form many kilometers below Earth's surface in an organic-rich rock called a source rock. If the source rock and the rocks above it are permeable, the oil and gas will rise upwards as they're less dense than the rocks around them. When the oil and gas reach an impermeable layer, called a cap rock, they stop. The rock under the cap rock, where the oil and gas are now trapped, is called the reservoir. The reservoir for oil and gas is similar to a confined aquifer. Remember, oil and gas can exit the source rock and move upwards only if there is sufficient permeability in the rocks, which, just like groundwater movement, means connected pore spaces or cracks. Sometimes a source rock is full of oil and gas but has no permeability, and most of the oil and gas remains trapped. In such cases, a technique called hydraulic fracturing, or fracking, is used to increase the permeability of the source rock, so it will release the oil and gas. Wells are drilled into the source rock, and then water and chemicals are injected into the holes at high pressures to both fracture the source rock and make it easier for the gas to collect in the injected water and exit. This technique is primarily used to release gas from shale. Pause now.